Hello everyone and welcome, whichever part of the world you are on at this moment. And before we start, it's important to mention that this session is previously recorded, but you are welcome to ask questions in the chat and we will try to answer them as best as we can. This is my cat. My cat has been a very good companion over the last 2.5 years in the pandemic. I'm actually in her house because, as you know, my house does not belong to me. It belongs to my cat, as any cat owner knows. And you also know that if Skynet takes over, which will happen, the cats are the only things that can save us from these evil machines. My name is André Melancia, and I've done some of these crazy sessions in the last few years, many of them in person, but lately, as you know, most of them have been done online. But I'm really hoping that this will change, and specifically in the case of Data Platform Summit, not necessarily virtual, hopefully there will be an upcoming edition where we can meet in person. So let's talk about the session for today. The session for today is machines are learning. That is true. And you should learn machine learning as well so that you know how to fight these evil machines. First of all, some thanks to Microsoft, and also a very special thank you to the organizers, to Amit, to Satya, to Arti, to Manu, to everyone for organizing this spectacular and epic event, which both online and in person is top in the world with so many people and so much diversity. Also, you know that if you provide feedback and things like that on these sessions, you are candidate to win some prizes, so feel free to give us feedback, interact in the sessions as well, talk to people, talk to me, talk to everyone else, and enjoy the conference as possible. Yes, it is online, but online is the next best thing. Hopefully next time it will be in person. And as mentioned, if you have any questions, you are more than welcome to ask them in the chat. We will try to answer all of your questions as much as we can. If not, at the end of the session, I will provide my contacts, and you are welcome to contact me in any other way. But feel free to keep the questions going, and we will reply via the chat as well. Okay, let's get started, and let's talk about machine learning and artificial intelligence. These are two different things that people usually confuse. Now, academically, artificial intelligence is actually the area of science that talks about Skynet taking over and having intelligent machines, etc. Now, I'm actually kidding. Artificial intelligence is an area of study that looks at machines and tries to automate many processes with machines. Intelligence is not really artificial, but if we consider in the last few years that many people were against vaccines and they were assuming that the earth was flat and things like that, so the level of intelligence in people is actually not that much. Remember, my cat, much more intelligent than these people. So with artificial intelligence, we need to consider what it really is. So let's take an example. Artificial intelligence, we've seen cars driving themselves, we've seen so many things like robots, moving around and things like that. But are they really intelligent? Well, the answer is actually no. They are not conscious in the sense that we know that we exist, etc. They have a predefined program. So let's assume that you are a developer. If you are not, just go with me. And one of the things that we'll see is that artificial intelligence is actually just a bit of programming. Okay, so you start an application, you have some programming, and the programming is a bit more dynamic. So it bases itself not just on the normal, line 1, line 2, line 3 programming. Well, it does, but it also reads into additional things. Some of them are actually part of machine learning. We'll get to that. But these things are actually getting information based on past experience, as an example. Okay, so let's try to see some example of this. I usually mention the maze example, and the maze example is, consider you have a maze, like an experience, a lab experience. And in that experiment, you have a mouse, and the mouse has to go all the way up to the middle of the maze to find some cheese or something else that the mouse likes. It's really bad to have mouse with a reputation that they only like cheese. They probably like other things as well. Now, the mouse will follow its nose. They have a nose. They will try to follow the nose to try to figure out where the cheese is and try to optimize the path. The mouse will not try every possible combination to find it because they use their senses to try to optimize finding the cheese. Now let's assume that we put a robot there, and in the middle we have an energon cube, and the robot wants to get that energon cube. It's also food for robots, and one of the things that we've learned in school, most of you probably had some algorithm classes, possibly in university, high school in some cases, and those algorithm classes usually teach you that you can, traverse the maze in many ways. One of them is depth first search. So you have 2 or 3 options. Let's assume, for simplicity reasons, you only have options left and right. So first of all, you take your left option, and then you are faced with another option. You can go left and right again, and in that case you decide to go again to the left, and the next one you go again to the left, and so on. So you try all left combinations first, and if that fails you backtrack 1 level, and then in the cross section you try to go right, and if that fails you go back again 2 cross sections, and then you go right on the next one. If that fails you go back again, go back again, go back again, until you are in the starting point, and instead of left you go right in that point. Okay, obviously this would be an example of a kind of a binary kind of graph, kind of a tree thing, left and right. These are a bit more complicated than that, but you get the idea. Now, this does not help you, because if you always start on the left, or if you always start on the right, if the cube is in the middle, you're always going to take a long time to find it, right? So it's not good. Well, one of the things you can actually do is you can use some intelligence based on previous experiments. So if you have a robot run this experiment a whole bunch of times, and the energon cube is always in a random place, the robot will try to figure out some patterns of where it is. So based on what we know from robots, they would probably try to go left and right, one of the 2 firsts. So we as humans, we never put the cube completely to the left or completely to the right, because they will find it very quickly. Now, by the way, there is other algorithm traversing, techniques, which are, for instance, you have horizontal search, in which you go 1 level, try all doors, go 1 level, try all of the next doors, go the next level, and so on. That could be good or bad, okay, but remember that artificial intelligence will probably go a bit further. Now, as I was mentioning, the robot will try to predict things, will try to base itself on previous experiments, and one of the things that they will probably find out about humans, and this is very dangerous for us, is that the humans typically use some predefined notions, okay? So for instance, if I ask you to choose a number between 1 and 9, okay, it can be 10, no problem, but let's say a number between 1 and 10, I can pretty much guess, so choose a number, and I can pretty much guess that you're not choosing number 5, because that's too obvious, that's in the middle. You're also not choosing number 1 and 10, because again, that's in the extremes. I'm assuming you're probably not going to choose an even number like 2, 4, 6, 8, because there's something wrong that humans consider about those numbers. We don't feel that they are random enough. So in the end, you are likely to get number 3 or number 7. Okay, number 9 is also not very typical because it's close to the end. So you're probably going to get number 3 or number 7. So if a robot can understand this based on recurring experiments, they will find where the cheese is, and they will take over the world. So that's obviously a problem. These kinds of predictions fall into the category of something called heuristics, and you probably heard of heuristics already. So the easiest way to explain this is that this is magic, okay? So the robots will get some information from somewhere, they will treat it as magic, and then they will decide based on that kind of magic decision where they should where they should take, their next steps to find it faster. Well, it can go right or wrong. Another example of logistics and even the use of artificial intelligence in these kind of logics is to use things like antivirus. So nowadays, you have a very big difficulty in trying to detect individual virus signatures. Consider that in 1991, for instance, this was like 1991, 1992, like 30 years ago, some of my first computers, we have antivirus, and at one time I actually printed the lists of all of the viruses possible, and I can tell you that the list was like 10,000 different types of virus. Now you cannot keep up with this. It's very difficult, and nowadays that number after 30 years is going to be exponentially big. Okay, so you cannot just base yourself on the signatures. You have to have trends. So a trend is, well, okay, so if there is some assembly codes in that executable file that will actually exhibit a behavior that has been seen in many virus strands in your computer, then they will consider that to be dangerous, and they will either block it, quarantine it, whatever they will do, right? So using that kind of artificial intelligence is okay, but before they did that, they had to use machine learning. So what is machine learning? Well, machine learning is a subfield of the area of artificial intelligence. So artificial intelligence is the whole thing, and specifically you have some parts. One of them is machine learning. Now, with artificial intelligence, this was very simple. So you had a simple programming that at some point in time said, please read the heuristics, which can be, as the example of the maze, which can be just doing a group by on the trends of where the cube was usually there, and then they will try to find the best way to traverse all the graphs, starting with those places. So the artificial intelligence, we might think that it is unpredictable. It is actually not. It's just normal programming. You can follow the programming, but it's at such a small level that the machines will process this millions of times, so it feels random. Now, with machine learning, it's exactly the same logic. It's still programming, and unlike artificial intelligence, because heuristics, it's not going to be deterministic. That means that if you run the same experiment over and over again, you get different results based on those past experience. With machine learning, you typically have, I'm not going to say it's full deterministic, so that means that if you run a training with the exact same data, that you get the exact same results on the outside, but almost very close. So it's statistically deterministic. Well, that means that, let's say you run a machine learning training, and that machine learning training is used to predict bank loans. So if you are going to pay your bank loan or not before they actually give the bank loan to you, so that they can decide if you are a good candidate to receive a bank loan. Well, there is one thing that's called accuracy. Well, there are other metrics like accuracy, precision, etc. I really don't want to go into those details at this moment. You are welcome to have a look. Different types of algorithms have different types of that quality metric. So it can be things like area under the curve, Spearman correlation, etc. There's a lot of names for this. Let's not get there. Another one, for instance, is mean root squared error. Let's not focus on that at this moment. So any of these metrics, some of them are good if they go up, some of them are good if they go down. So accuracy is good if it reaches close to 100%, which is very difficult. By the way, accuracy and precision, okay, these are not exactly the same thing. If you are in a language like Portuguese, like me, these two words translate the same way in Portuguese, but these are actually slightly different, okay? In general, let's call it quality, okay? So the quality of the algorithm can be going up like close to 100%, or can be going down like mean root squared error, that the value closer to 0 is ideal, because being closer to 0, that means it's closer to detecting it. It's like the distance. In this case, it's not exactly a mathematical distance, but close enough. It's like the distance between the correct value and the error value that you predicted, which is a small error. So mean root squared error would be closer to 0 would be good, okay? So the idea here is that when you have machine learning, the idea here is that the quality, whether you run this 1 time, 2 times, 3 times with the same data, on average, the quality will be similar. So let's assume it's an accuracy for that bank loan. Let's say that you get 85% accuracy, okay? Not necessarily bad, okay? One time you get 85, the other time you get 86. So statistically, it's kind of the same thing. really good, no problems. Okay, now we have some examples of algorithms that I'll talk about in the next few slides. But for now, let's just mention that in terms of programming, it's reasonably close to deterministic, as I mentioned, to actually run machine learning. But it's not perfect. An example of why this is not perfect is that you might be running this based on a time limit. So let's say that you can run training up to X number of hours, X number of minutes for each training, if you're running multiple trainings, etc. And that time limit, depending on how the computer is running, might actually finish a few seconds, a few minutes, a few milliseconds even sooner or later, and that can make a difference. So statistically it will probably be the same, but not as perfect. Okay, so in terms of algorithms, should you be programming those algorithms? Probably not. Okay, so these are for genius people. It's not the case with me, and in my case, I'm a simple developer, so it's easy enough for me to just use that machine learning algorithm. So it's basically a library, and you write 1 or 2 lines of code, and you can just use that machine learning algorithm to predict things. Okay, remember, it's like 1 or 2 lines of code to do the prediction, 1 or 2 lines of code to do the training before you actually do the prediction. Okay, and the big step, and this is the part that I want to emphasize that's very important, is that 80% of the success of your endeavor doing this is getting good data. If your data is not good, and if you feed it to machine learning, the thing will be terrible. Okay, so I'll give you an example of this. If you go to Facebook, if you report a bad post, like we've seen some bad posts during COVID and during the current situations, etc., in many cases you report them and Facebook says, oh, there's nothing wrong with them, but you clearly know that this is completely wrong. These are criminal posts, these are ignorant posts, etc., evil posts in general. But then sometimes you write your own posts saying thank you, and this has happened by the way, saying thank you or saying some idiomatic expression in your own language, and suddenly Facebook blocks you for 30 days because you did something terribly wrong. And this is not just some human on the other side that doesn't like you. This is actually AI gone terribly bad, because they started with data that was completely wrong to begin with. They did some machine learning training, and then the machine was like RoboCop doing the wrong way, which killed the humans instead of saving them, right? So let's not go into Asimov's laws of robotics, but the idea here is that in the case of that Facebook thing, they actually condemned the people that said nothing wrong, and they didn't say anything to the wrong people. And the reason for this is we know this from leaks on Facebook, is that when they hire people, they hire the people that were trending to be susceptible to this, because they received very little wages, and they did this, so they analyzed each of them, and the humans would say, is this okay, is this not okay? Many of them, for instance, were Trump supporters, some of them were COVID deniers, and some other things as well. So that means that when they fed the algorithm with information, most of that information was wrong to begin with, and the machine, which is not their fault, actually learned from it. Okay, now this is machine learning. Let's go just a little back to artificial intelligence to take this example. You probably remember a few years ago that Microsoft created the bots on Twitter, and within 2 days that bot became completely racist, completely insulting to everyone, because someone fed it wrong information. The bot had only one directive, like HAL 9000 only had one directive, which is to learn, and in this case that bot on Twitter actually learned that it was okay to be racist, it was okay to be, insulting and genocidal and things like that. So we saw that. So within 2 days only, they killed it. Now, we know that this was people from, Google and the competition, etc., that actually fed a lot of bad things, so that the bot would actually learn all of the wrong things as possible. But part of it was also human nature, because human nature, if you go online, a lot of people will try to attack you without saying anything. They usually say, ironically, that if you go online and ask a question, no one will answer it. No one is nice enough to answer it. But if you have a separate profile, go there and attack yourself in this case with the other profile, everyone will come back to it and try to defend you because someone attacked you, so they have to do the opposite of that person and they will try to defend you, and vice versa. Okay, this kind of thing happens. Now, let's have a look at some algorithms themselves, and typically we divide this into two parts, okay? So the supervised algorithms, that means that, let's take the bank loan. So you had a few fields. Those fields can be, age, they can be if you are married or not, what kind of job do you have, how much money you make, those kind of things, how much kids you have. They never ask for pets, which is ironic. But in any case, one of the columns, typically the last column, and typically they have the column written as Y. So input columns are X, output columns, so the last column, the results, is usually Y, and this is typical in any graph, X and Y. So the Y column would be a true or false result. So yes, they paid the bank loan. No, they didn't pay the bank loan. Okay, so supervised is a way where you provide the information, the input information, the X information, but also the Y, the output information. Okay, so when you learn, you already know the answer, and you are going to train a model to give you those kinds of answers. Okay, and things like linear regression and regression in general, classification, those are good examples of where typically you have supervised. Okay, typically, I mean typically because these can be different. Okay, and then in unsupervised, things like clustering, association, in which you define things like, oh, if I buy toilet paper at the store, what kind of other things should I buy? Oh, if you buy things like wine and toilet paper, is that related to each other? Well, probably not, because you're probably doing your shopping once a month and you buy the whole thing in bulk. But yeah, I know what you were thinking when I said this. Okay, imaging and anything related to processing of things that you cannot predict what they are. So imaging, video, audio, etc. So those things typically don't have the results when you are training them, okay? Now, one of the things that you can do for images, but technically you can do for a lot of the other algorithms as well, is that you can use neural networks, okay? And neural networks, deep learning, etc. And that typically gives you a very good quality, but it also requires you to have a lot of processing capability, okay? So we'll get into this in a bit. Now, remember, machine learning is not perfect, okay? This is a good example. So you have a very nice cow that provides you with cow juice every time you need it. And this one specifically, it's a very big one because it has a length of 5 meters, okay? The height seems okay, has a length of 5 meters. Well, if you are human, you feel that there's something wrong because this cow is like a giraffe. It has a very big neck. But if you are a computer, this feels perfectly normal because there's an object in the middle and they are trained to ignore the objects in the middle, like some human, something else, but they feel that the cow is just too big. Well, yes, there are ways to get around this. So a cow should have a minimum and maximum height, probably a minimum and maximum length, or at least some proportions that make sense because the image might be far away. But in any case, the machine might get things wrong. And we'll see one or two examples of where the machine does get things wrong. Okay, let's have an example of how machine learning works. Quick example. And these things that you see here on the right, these are copy-pastes or screenshot from Azure Machine Learning workspace. We'll get into that in a second. But a typical workflow, and remember that I mentioned that the trick is in the initial data. If the data is okay, your training will be good. Oh, 1 second. So you start with some data. So a data set, it can be a file. You can get this from, I don't know, SQL Server, whatever it is. It's data, okay? And data can also be, it can be tabular, but it can also be like pixels in an image and, sound, samples of sound, etc., okay? Now, you process the data, so split, normalize, etc., some kind of processing. So let's say if you are a supermarket and you are in the year 1950 and 2 people are born, and then in the year 2000, the first person buys product X, can be a chocolate, no problem, okay? So that product X was bought in the year 2000 by person 1. Person 2 in the year 2020 bought the same products, okay? So again, a chocolate. And are these people the same in terms of profiling? Well, these are not the same people. Okay, an example of that is if one of them actually bought the product when they were 50 years old, the other one bought the product when they were 70 years old. Okay, so it doesn't really matter what age they are today. It matters what age they were when something occurred. So when that record occurred, the buying occurred. Okay, so in this case, if you have things like you might want to normalize the data, process the data, convert the data in some way. Dates are usually an example, birth dates, and you typically convert it to age at the time of the person doing something. Okay, so in this case you convert the age to 50 and 70 respectively. Okay, and in some cases it might make sense to aggregate that age into age groups, like groups from 0 to 6, so kids that don't know how to read and write, 6 to 10 primary school, 10 to 18 high school, up to 25 university and getting drunk and things like that, and then 25 all the way up to 65, maybe in groups of 10 each. You have all of the adults working, and then from 65 on you have the retired people. For instance, if you are doing medical stuff, you might have to from 65 on you might have to divide into more age groups, because it might make sense. If this is medical, if this is something else, probably not. Okay, but those age groups are probably easier for machines to actually associate between the users, because if you are 11 or 12, doesn't really matter. You're pretty much the same profile. Okay, but if you are 25, it's completely different from being 11. Okay, now you clean up all of your data, you prep the data. Feature engineering is choosing the columns, so features are columns. Okay, remember that when you do BI, instead of columns you have dimensions, and you have measures and things like that. So here they're called features. It's a column. Okay, it's a field. Okay, so you do feature engineering, you choose the fields that make sense. For instance, you want to remove all of the fields that are personal identifiable information, like ID number or passport number, something like that, or even the name of the person. So the fact that I'm called Andrea makes no relevance in my shopping profile when I go to the store, so it shouldn't even be there. Okay, that makes sense. Okay, other things like nationality, like age, etc., those might make sense, because a Portuguese guy, I like certain kinds of food. If you are in India, you might like different kinds of food, and so on for the other countries. Okay, so anyway, then you go and do your training. So training here, in this case, it's actually a hyperparameter training, so you are actually running a lot of trainings at the same time, but all of this can just be a single box of doing one training. So you start by choosing the algorithm. So here you see neural network regression, but it could be something else. Doesn't really matter. It could be something else. Okay, and one of the ones we talked about, some of the ones we will talk about. Okay, now after this you have a few of these. We'll get to this in a second, and you do it using any of these categories, but you use some techniques in those algorithms like deep learning, neural networks, etc. For that. Now, once you do your trainings like single training or hyperparameter tuning training, which requires multiple trainings separately, each of them with separate parameters into those algorithms, so you can define, let's say if you have a decision tree, you can define how many levels you want on that tree, or how many trees in total you want to have, or something similar to that. Okay, so you want to do different kind of logic, so you can do different hyperparameters, and then one of them will give you the best quality based on what we talked about before, and then you can choose which one is best and start to use that one for the actual predictions. Okay, now once you do that, you do the scoring. So for each individual model that you might get more than one. For each of them you need to do the scoring and figure out which one is best. Okay, so this one is best. Sometimes you have actually do it with multiple algorithms as well, because trying just one is not good. So we'll talk about things like AutoML that do this automatically and choose a lot of different algorithms and hyperparameters, and then they will give that to you automatically without you having to do anything. Okay, now but the scoring takes place when you analyze what's the quality of that model. So it's good accuracy, so 85%. Oh, but wait, this is 86, this is 87. So you typically keep the best one. Okay, there might be reasons why you don't. So if these don't target specific groups of people, and this is a different range into responsible AI. Let's not go into a lot into that at this moment. But in any case, if the group, if the accuracy is very good, but at the same time some specific demographic group fails miserably, the training is not good. Even if the quality is better, you need to go back and choose a training that might have less quality, but overall treats treats everyone in a more equal way. Okay, so have a look at responsible AI. You can go to the Microsoft website, responsible AI. There's a lot of information about that as well. Okay. Anyway, once you do the scoring and the testing, so this is comparing to some results, and I didn't mention this yet, but let's go for this. So this split data here typically divides the data into two parts. Let's say 80%, 10, 70, 80, 90% to the left to do the training, and the remaining part, average 20%, 30, 20, 10% will actually be doing to do the testing if the model is okay. So they use the remaining data to test the stuff, which works okay. Now, once you do all of that, you compare all of them and evaluate the model and compare which is the best one. Okay. Now, next up, we deploy a predictive web service. So it can be a web service, can be a different thing. You can deploy your model into an app and use it on a phone directly without even communicating to the internet. You can associate that with an IoT device if you'd like. Nothing's wrong with that. Okay. But you deploy it somewhere. Okay. And in many cases, this is usually called inference. So you typically deploy this into an inference cluster or an inference, compute, location, machine, whatever, right? In many cases, these are containers, okay, like Docker containers. Now, last but not least, very important, after a while, there is some data drift. That means that the quality is lost. And an example of data drift is pandemic. In the last 2 years, every machine learning model that you had, because, everyone changed their way of life, machine learning models stopped being obvious. So they lost a lot of accuracy. They had to retrain a lot of things all over again. So from time to time, depends on your business, but maybe every 6 months, every 3 months, maybe more, maybe less, we don't know. Depends on your business. You need to retrain them again. And this is easy. Okay, let's have a look at quick algorithms and then we'll do a demo. So algorithms, things like regression. This one is the much simpler one. Now, regression in general, in the category of regression algorithms, that means that you are searching for an individual value that's a continuous value. So you typically define a function or something like that defines the answer for you. So let's consider something that looks like this. So you have a line here. This is a linear regression in this case, what you see here. It's literally a line, and the formula for this is very obvious, okay? This is something that you learn in school, and this is probably the only algorithm that you can actually program yourself. Everything else is very, very complicated, okay? It's very difficult to understand. Even very big experts look at the model values, etc. They don't understand what they mean. But this one is easy, because here, to actually draw this line, the line is based on the average of the distance of these points, so to minimize the distance and the error between all of these points. Okay, there's a mathematical definition for this, but let's not go there. So in this case, what you get is a line which is a plus bx, okay? So a is this value all the way up to 27, 28, whatever the value might be. So it's the y-axis extra, so a plus something, and bx is the inclination of this curve. So if you define the values of a and b, and these will be our model, so two perfectly normal numbers, okay, you can compare that if you try to get 60 here. So let's say that you have you send a request for a prediction, and your input values are 60 here, okay, and then when you go to 60 here, sometimes the value can be one of these on top, like one of these on top that might be completely wrong, but in most cases, most of your values will fall close to the line, so your prediction will be something like 50 as a y, okay, which is okay. So is this correct or not? Well, you have things like mean root squared error, Spearman correlation, etc. to tell you if these are terribly wrong or very accurate. Instead of a line, you can actually have curved functions to do this. I'll show you one or two examples. What to use this for? Well, you can predict a lot of things, like, for instance, things like the weather. And remember, the weather is not very good because, after a few days it becomes chaotic, so it's very difficult. In terms of economics, it might make sense, but not the stock markets, okay? But biology is a very big thing. Some trends, except if there's irrational human behavior that we know clearly exists, okay? And then you have a few other types of lines. So let's give you an example. This is how it is trained. So you see here on the right that this is actually a GIF somewhere here. I got this out of the internet, no idea what it is for, but in any case, what they do is that they train this a bit up to the point that they adjust the values, the formula for that line up to the point where it's a reasonable value, okay? And in many cases, you can even have not 2D, but 3D, 4D, 5D inputs that give you a result. And in this case, the red stuff that you see here is actually based, the error is between this plane that you see here, which might be your result, and the error is the distance, the shortest distance between your real value and the actual prediction, which is the plane. Okay. Remember, this can be a two-dimensional plane. This can be a cube. This can be multi-dimensional things that we cannot see. Okay. Anyway, a few examples of things gone terribly wrong. So bias. So you have bias here. So if you draw a linear regression, this is going to go terribly wrong because you're not going to find the right values here. Okay. So a linear regression, all of these errors will be too big to be reasonable. Okay. Another example here is a good fitting will be this, this function here that detects this value. So your model will generate this function. However, if you draw a straight line, this will be terribly wrong for many values. If you spend not, let's say, a few hours or even a few days in some cases, but if you spend months or years fine-tuning the formula for that line, you might get this formula, which is great. But this formula is based itself, it's overfitted because it's based on specific values that you have now, not the values that you might eventually have. So you're basing yourself just on the values for the training. And then the next value will be somewhere in the middle of this, which is a good average, but then your formula will give it a huge error. Okay, so for instance, this one will be okay. If you put a number next to this where you see the mouse here, this will be perfect. But if you put it here where you have the mouse, it will be completely terrible. Okay, so a good fit will not be too little or too much of this. Okay, so and this is an analogy for life as well. So don't do too little, don't do too much, just do enough. Okay. So beware of monsters. So let's say you have some points that look like this. If you decide to do an average of this, and this is the Datasaurus is very famous online, but if you decide to do an average of this, this is what you get. Okay. And you have other examples of other types of Datasaurus in which your result was either zero or a flat line or something like that. Okay. Because remember, one of the points on top will actually round up to the points in the bottom, and they will cancel each other out, and then the end line will be very, very similar. Okay, so please be careful, because when you get your data, you might get wrong expectations from your data in some cases when you do some visualization. Okay, now logistic regression, we were talking about bank loans. Okay, I usually have an example that I use this thing for. So consider that this is the amount of time that you spend studying for an exam, like 3 hours, for instance. Okay, and in this case, if you are a yellow, you pass. If you are a blue triangle, you fail. But you can tell that with logistic regression, in this case, a 2-class model, you can actually get the values like this. So most of the values will be well predicted. So this is you spend more hours studying, you probably pass. You spend less hours studying, you probably fail. And some cases you study very much and still fail. Some other cases you study very little and you still pass. Okay. Now this line here is kind of vertical, but the correct one would actually be horizontal. I copied this from the internet. I'm a very lazy person. Okay. So the line would be more horizontal than anything. You can define a threshold. Now default is usually 50%. Okay. When you do a prediction, but if you do ask for a bank loan, prediction shouldn't be around 50%. You should analyze what makes sense. And in some cases, because you are human, let's say it's a bank loan prediction. If you say a person has 59%, another person has 49%, the other person has 51%, and then in that case, one of them gets it, the other one doesn't. And then you might actually get the wrong ones, and the one with 51% will actually be, a criminal that actually doesn't pay for this, and the other one pays for this because they are honest. Okay, so you have to have some human interaction here, and in many cases, it's just easier to say, up to 40%, your computer says no, from 60%, computer says yes, and then somewhere in the middle, get the human to decide from those middle 20%. Okay, so you have a gray area there where the human actually decides. Okay, now if it is a 2-class model, true or false, A or B, something like that. Results are something between 0 and 100% as the results, okay? And then you specify that threshold to determine if it's A or B as the results. Yes doesn't have to be 100%. Yes can be 0%, depends on how you do the machine learning. If you do a multi-class model, so 3-class, 4-class, etc., that means you have to predict A, B, C, and D, okay? So which one will you choose? Will you choose A, B, C, and D, or something like that? So this can be, let's detect the nationality of the person. So is it Portuguese, Indian, Chinese, something else? So you have to detect the nationality of the person, so that would be a multi-class results, okay? But remember, unlike the other one, which gives you a number, a continuous number, like temperature, etc., this gives you a class A, B, C, or D as the results, okay? So next up we have, and be careful if you exaggerate, same as the slides before. If you exaggerate, you might have a lot of issues trying to have the data confess to things that they're not actually doing, okay? This is kind of CIA-style torture to your data science. Now, we talked a little bit about this in toilet paper and things like that. Clustering is when you have, let's say, 2 or more dimensions, can be 3D, 4D, etc., and then you try to group them like this, okay? The most typical algorithm is k-means, and what they actually do is, that algorithm hasn't changed much since the 70s, even before I was born, and what they actually do is that they try to select a certain number of clusters, and then they will try to move those round circles. They're not actually circles, but the association of each point to each of these clusters as best as they can. They do this iteration until it stops. When they stop iterating, that means that they are the most ideally placed, and then you can associate that with this group of people, that group of people. Like in a supermarket, you can use this for cybersecurity as well, so to detect trends in some scenarios, etc., and many more, okay? So shopping trends online, in person, etc., even social network analysis like Facebook, etc., there used to be amazing apps to do this, that since the privacy things in Facebook started, which I'm not against, but some of these things that were actually very fun to see with some apps that Facebook allowed, you cannot do this anymore, okay? You have to extract the data by yourself manually to be able to do this. You have to crawl it, okay? So anyway, clustering with k-means, you start with something and then you generate the results. Very easy. It can be something like this, and then you generate clusters like this. So these are not as isolated as those, okay? And sometimes you get 3D clusters, which can also happen, okay? 3D, 4D, the number of dimensions that you define. Okay, now let's talk about techniques. So we have a lot of algorithms, but each of them, let's say a regression, one of the options for regression is using decision trees, okay? Decision trees, decision forests and stuff like that. They use anything related to trees, okay? Related to anything green. So one of these is the decision tree, and this is very simple. So the actual computer will start building up these trees. So they have information like, let's say you start with this information at some point. No, you don't start with the information, but they accumulated this information. Like, I have my cat. Is it a mammal? Yes. Do people use it as a pet? Yes. So the computer assumes, based on the information that the computer has, that you have a hamster. But then I tell you, no, you have a cat, and it meows and things like that. So the computer says, what's the difference between a hamster and a cat? And you say, look, a hamster doesn't meow. So next question that the computer adds here is, does it meow? If it says yes, it's a cat. If it says no, it's a hamster. Okay, so now the computer has learned a bit more. This is literally just adding 1 or 2 lines into a table. It can be a table structure if you want to. It doesn't have to be a table, but it could be a table. Okay, now, is it a mammal? Yes, yes, yes. Now I'm talking about, let's say, a dog. Okay, does it meow? No. So again, you have a hamster, but no, I have a dog. So what's the difference between a hamster and a dog? And then you add another question and so on. Okay, now these trees grow, okay, with the information that's being fed with all of the inputs that you have. And once you have all of this, then you do predictions based on having these kinds of trees, okay? And although this is not really how it's done, think about the tree as you are going to follow all of these questions. Sometimes you end up not being in the tree at all because the tree doesn't relate to you. Other times you end up in a small part of the tree. tree, okay? And because you are doing a lot of trees, consider that you know SQL joins. Think about adding, think about trees as tables, and then you join all of the results of each tree together like in a kind of a join, okay? And whatever is common is probably going to be your answer, okay? This is obviously not the same as a SQL join, but think of it like that in a simple way, okay? So anyway, there is actually an example of this, 20q.net. It's a website. You can try to see how decision trees work by answering a few questions. Very fun, but because they have so much information, 20 questions are not enough. Last time I tried it, they had like 32 questions to actually be able to detect what it was. They weren't, 20 questions were not enough, okay? But please try it. It's actually quite a fun. And then they will ask you not just yes or no, they will ask you other types of questions, and they are treated slightly differently by the algorithm, so not exactly as basic as the one I mentioned. Sometimes they don't say yes and no, they sometimes do it by percentage and things like that, okay? Anyway, just to mention that you can use neural networks as techniques for this. It's like you need to spend weeks actually learning what each of these things actually does, and these are all independent. They talk to each other. It's crazy, but let's not go there, okay? So this is how you have things inside. You don't need to know this. You just need to have a black box, fill some inputs, get some outputs, and you are done. But internally, you have these kind of things, okay? Now, to give you an example, let's say you are doing regression. So simply detecting a value like what's the temperature going to be tomorrow, okay? You can actually do linear model, so small data sets and probably small memory footprint in RAM. So you can do linear regression here or Bayesian regression, which Bayesian uses a very nice technique to actually optimize some things. I'm not going to go there a lot, but it is interesting. You can use decision trees, decision forests, decision jungles, etc. You can actually use neural networks for that same regression as well. Obviously, these neural networks, etc., this neural networks will be much more accurate than the other ones, but it has long training times because it requires a lot of resources and a lot of time to actually process, but they are more accurate than, for instance, linear regression or Poisson regression, etc. Okay, so you have more up here. Just go to aka.ms/ml cheat sheets, okay, and this jumps somewhere into GitHub and you are able to see this. Possibly they will update this on a regular basis, okay. Anyway, anyone can do this, okay, this is fun, and in our case, I'm just going to leave this slide here. Feel free to come back to this later on if you want to have a look. We'll focus on Azure Machine Learning, but if you are using Python, like most things in Azure Machine Learning, you can actually use Spark clusters, and they are available in Databricks, in HD Insight, in Synapse Analytics if you want to. You can use R. In some cases, you can use C# and ML.NET if you want to. Apart from machine learning, you also have things like cognitive services, which are web services that you can do face recognition and, you know, convert speech to text, text to speech. Amazing things, but let's not go there today. Feel free to have a look at some videos that I have online, links on my website to have a look at some of these things, even the other ones like Synapse, etc. But today we'll focus on machine learning, okay? Remember, no matter what programming language you use, the trick is not the programming language. If you don't know Python, if you don't know R, if you don't know Scala, for instance, or C# or whatever, doesn't really matter. The trick is in the libraries. In most cases, you'll do 1 or 2 lines of code and things just work, okay? So Python is a very ugly language, but it works really, really well. Okay, now we have time for a demo, and let's have a look at some demos for now. Okay, now first of all, Azure, you go to azure.com, you go here. How do you get to use this for free? By the way, most of the things I'm going to show you, if it is code, you can do this on your own computer. You don't really need to use Azure, but you know, Azure makes it very simple because it already has machines with installed software and stuff like that. Okay, so you can go here to free account, and you have some certain amount of credit or equivalent in your currency that you can use, and some free stuff, etc. If you actually go /students, and if you are university students, you can actually get free credits that every year repeats, okay? Something like $100 every year. This is not a lot, but you know, it's better than zero, but you still get the free account if you want to, but that requires a credit card, even if you're not being billed, okay? Once you set up one of these, you can actually go to your dashboard, okay? So this dashboard is in portal.azure.com. So again, portal.azure.com here, okay? And then whether you have a dashboard here or your home, I like the dashboard, you can click the plus sign, or here on top with the sandwich menu, the plus sign, and then you can actually say, let's create an Azure Machine Learning. So Azure Machine Learning, okay? So because a lot of things might be called machine learning, make sure it's coming from Microsoft, and then you say create, and then let's create a resource group, and that resource group will be Skynet will take over everything. Okay, the X is for me to just remember to delete it at the end of the day. Okay, so workspace name, let's call it NDML. So for machine learning, and West Europe is okay. So I have to put this in a certain region. Okay, and storage accounts, etc. You can have one that already exists, but I'll create new ones. Container registry is when you want to deploy images of containers to do predictions, etc. You can actually add a container registry, but by now let's do the defaults, make it public, etc. You can improve security. This is not the focus today. And then you say review create, and then you create this thing. Okay. Now I did mention that this was a recording, so it will take a bit of time to run this, but we of course can do like a cooking show and pretend that this isn't you put it into the oven and suddenly this is done. Now let's go to the resource, and you have a bit of information. So this is the same as you had in the other wizard. What you want is to click on Launch Studio. This is the same in Synapse Analytics, Databricks, etc. And please remember that all of these things that I just mentioned can actually talk to each other. It's quite amazing. Okay. Now let's have a look at this, and you have your home here. This is fine. You have some notebooks, so you can do code with Python, technically with R as well, but the full support for the amazing SDK is only in Python. You can do AutoML. We'll get to that in a second. And then you have here a few other things. So these assets are the results of running things. So the Azure Machine Learning SDK receives information every time you run one of these three types of machine learning, or even just running things. It doesn't have to be machine learning. It can just be an ETL process to process data if you want to. It doesn't really have to be machine learning. So you run all of these three, and then the results will show up here. Now, data stores are any source of data that you want to get. So you can get that from blob storage and data lake store. You can get that from a file share, SQL database, or MySQL, MariaDB, and Postgres. So either way, okay, data store is pretty much just calling a reference to a certain location, like a connection string, okay? And then each of those stores, these are the default ones that come along. Each of these stores can actually put some data for you, and in that case you get the data by getting it here. So we don't have any data now, we just created this. I can create it, but I'll leave this for a second. Okay, now all of these jobs are things that ran. We don't have anything yet, but we'll get to that. So was the other one. So let's run something first and then see the results. Okay, now we have a few more like linked services, data labeling, etc. These are also interesting, but this is not a focus for today because we have limited time. So let's have a look at creating a compute instance. What is this? Well, it's basically a VM that has a lot of things installed. So, and the VM1, it could be CPU or the N type of virtual machine. So instead of D machines that you have, just go to azure.com/pricing, look at the pricing for virtual machines. The N type virtual machines, which have NVIDIA and other GPU boards, can actually be used to improve machine learning, but they're also more expensive. So let's keep it simple. Let's keep a small machine. DS3 is small, price is small, so let's keep it reasonable. Next. You can enable SSH, you can put it into a different virtual network for security context, etc. But for now, let's ignore it. Let's keep it simple, okay? Startup shutdown schedule. Well, I don't need this for now. I'm just going to create it, okay? So it says it's creating, so that's fine, okay? And we have our compute clusters. So we need a compute cluster, and we can create a compute cluster. But once you do that, you choose a location. It can be in a different part of the world if you want it to be cheaper, for instance. But then you give it some name here. I'm not going to do that. And then then you specify the minimum and maximum number of nodes that you want to use. Now, Azure Machine Learning SDK will automatically turn this off if you're not using it, or associate with a certain number of nodes that you need and turn off the nodes as you stop needing them. Okay, so this is automatic. Okay, you can also deploy things to inference clusters. So inference clusters here could be, in this case, a Kubernetes service, but if you do it with code or with some wizard that you have here, you can actually deploy to Azure container instances, which, unlike Kubernetes, which is a big infrastructure with a lot of virtual machines as nodes, with Azure container instances, it's just one single container floating around in the cloud somewhere. You don't know where it's hosted, but you don't really care. It just works, has an address, just works. As attached computes, you can also associate yourself with, as I mentioned, Kubernetes as well, to do processing there as well, HD Insight with Spark, Hadoop, etc. Databricks, Data Lake Analytics, which is kind of obsolete, but you can also associate yourself with Synapse as well, so Spark using Synapse. So and you can create your own virtual machines if you want. Technically, they can even be in a different cloud, so these actually work. Now let's have a look at AutoML. This is the simplest one. Okay, so you go and create a new AutoML job. Okay, and you need to create a data set first. So let's go. You can download it if you want to get it from one of these data stores, like a database, from a web, or open data sets. Okay, the simplest one is the diabetes data sets. Let's click on next. Get it some name. Name is fine. Next. Okay, and let's have a look at what it looks like. Okay. So this will take just a second, and if you click on refresh, you can actually click on this, and you have a lot of values. So input values will be your age, your gender, body mass index, blood pressure, some other metrics, I don't know what they are, and then Y is the result. So you have to be, to detect diabetes, you have to be between 90 and 120 or something like that to be okay. So you have a value which is a continuous value, so we're clearly doing regression to find this. Okay, so I select this here, I go to next, and then this will get me here. Give me a second. I'm going to create an experiment, and diabetes experiment 1, target column Y, compute cluster. Oh, I need a new compute cluster. Okay, so I could have created one there. Location West Europe, size reasonably small. Okay, next, compute name and the cluster 1. Okay, I make different names between the two, so number of nodes can be 2 or 3 to make it fast. Creates, and that will create the cluster. Once the cluster is created, I can click on next and run it. Okay, so this will take a bit of time, but I can click on next and run it. There's an additional settings. I'm going to skip those settings for now, but you do have some additional settings that you can try to actually improve this. So let's do the same thing again, and let's do the cooking show technique, and let's come back to this just in a few seconds. We are back. So now we have a compute cluster here. We click on next, and then we specify regression. We have to use regression, but it could be classification, time series forecasting, or you process natural texts, or even computer vision, for instance. Additional settings are available. Featureization is handling each of the fields. Additional settings as well. You click on next, and then validation. Let's keep it automatic. This is fine, but you can do some validation, especially if it's unsupervised. But let's say a test split, 10% is fine. We talked about this, and let's click on finish, and let's have this run. Okay, so this will take a certain amount of time, okay, and it will actually run. So we'll see what happens when this actually runs. So if you go here for jobs, this will actually start to run. We have to wait, and then the result will show up eventually, okay? Let's, again, freeze the recording and see what happens. And welcome back, everyone. So after taking all of these things out of the oven, this is the result. So you can go here to AutoML. You have an experiment here called diabetes. Let's have a look. And what we actually get is it says completed. Now this took a bit of time, like 40 minutes, 50 minutes. That's usually the normal amount of time. We can actually go here to see child jobs. Let me just say that some of these got canceled. This is normal because if they underperform, they get canceled. But one of these eventually got better, and this is the one. So model explain here. This has extras and has a nice star as favorites. So this is the result that we get. And we have some values here. So you get values of variance, mean absolute value, etc. So all of these were the results that apparently were the most interesting ones. So one of the things we can do is we can actually go here and take that model, save the model. So we can actually download the model if we want to, save the model here into register model into here to the list of models, or we can actually deploy that model as a real-time endpoint. Now today we don't have that much time, but just for you to know that it is possible. Last but not least, designer. You can actually go to the designer and see anything that is graphically based. So instead of doing things with AutoML without your control, you can go to graphic based things. You can also go to notebooks as well. Let's go for samples, and you have a lot of samples here like tutorials. Try this one, image classification MNIST database, which is actually quite nice. And just clone the whole thing. Click here, clone, and that will be available here in your files. And then run part 1 and part 2 and try this for yourself. In any case, because we are running out of time, if you'd like, you can see some more details about this, have a look at some of the other sessions. And if you go to my website at andy.pt, you can actually see some of these things as well. So special thanks to the sponsors and especially to the organizers that organized this. So thank you very much to Satya, Arti, Manu, and Amit as well. Thank you all. This has been amazing. And well, yeah, that's it. Thank you all for being here, and thank you for watching, and hope to see you next time, maybe eventually in person.